Okay? This is what you see in your book if you were to look at section 1.6 for composition of functions. I show you this, however, I don't think it's necessarily the most clear picture of what composition of functions are. The thing I want to point out in this one is the notation that asks you to do a composition of functions, and that's written here in the middle. It says the composition of functions f with function g is this, and the notation looks like this, f and then a little open dot and g. And it can be written a couple different ways, parentheses around it, no parentheses around it, doesn't really matter, but that's a composition of f of x of g, okay? F of g of x. The other way that this can look, which I think is actually visually more explaining of what's going on, is it can be written the exact same way, saying f of g of x. And doesn't that look like you're plugging g into function f? That's exactly what a composition is you're taking g and you're plugging it into all of the x's of f. And those are asking you to do the exact same thing. F of g of x, this is f of g of x. That's how it's read, but this is your new notation, that little open circle. People will sometimes confuse that for a multiplication. You saw a multiplication in your warm-up. That is a filled-in dot. This is an open dot, and they mean to do different things. Okay? So we'll talk more about the domain, and again, this picture is supposed to explain that. I don't think it does a great job of doing that, so we will talk about that in just a second as well, as far as what our domain of our composition is. So we're going to do a couple examples using those two functions at the top. F of x is going to be 2x squared plus 3x minus 5, and g of x is going to be x plus 7. When you do a composition, the order matters. When you write out f of g of x, we are going to use this function. So I'm going to write out 2x squared plus 3x minus 5. But instead of x, I'm going to plug in g of x. Okay? So I would have 2, and everywhere there's an x, I'm going to plug in the other function. So you can see right now this is f of x, right? But I left a space where all the x's were. And where the x's are, I'm now going to plug in x plus 7. And then we just clean up the way we know how to clean up. And so on this one, remember that if we have a binomial squared, x plus 7 squared, I need to do that first and then distribute. Write it twice in FOIL. I need to distribute the 3 all the way through that. Oops. Okay. So we'd get x squared, 7x plus 7x is 14x. Now 21 minus 5 is 16. Distribute that 2 through. And then finish out by combining my like terms here. And that would be my composition. F of g of x. Plugged g into f, cleaned it up. Okay. So like I said when I started this one, order matters. I am not changing what f and g stand for. They're still the same functions we see at the top. But on the second question, I'm asking it the other way around. Do g of f of x. So again, we are always going to write out that first function, plug in the second function. So I'm going to write out g, which is x plus 7. Wherever there is an x, I'm going to leave space to plug in that other function. So this is g, x plus 7. And where I left that space, I plug in f of x. 2x squared plus 3x minus 5. I'm plugging it in wherever there was an x up here in g, which is just that one spot. And then I clean it up. Well, there's not a lot to do to clean this one up because there's no foiling to do, there's no distributing to do, there's just combining like terms. And I combine the negative 5 and the positive 7, and we get 2x squared plus 3x plus 2. Any questions on that? Okay, now, These can get a little bit weird or can get multi-layered, so I just want to give you some other ways that this can look. You can be asked a question such as g of x. And that seems weird, right? But you just follow the same pattern. So we write out function g, and everywhere there's an x, we plug in function g. Okay? So I write out x plus 7, and wherever there was an x, I'm plugging in x plus 7. So I can do a composition of one function, plugging it into itself, essentially, cleaning it up. Well, 7 plus 7 is all I can do on this one, and we get x plus 14. Any questions on that? Okay. So I want you to try this one on your own, and I'm going to give you the first two to do, and then we're going to talk about the last one together. So given that f of x equals 2x squared minus 1 and g of x equals x plus 3, do f of g, and then do g of f. And I'll just be around to help. Just stop here. Yeah, you don't even need to do that. This one, instead of plus, it should have been distributed through that. Yep. Correct. All right, so you were supposed to do f of g and g of f. Let's look at our setup here. If I write out f, leave a space where there was an x and plug in g, it should have looked like this. Do the same thing for g of f. Okay, that was your setup on each of those, and then the cleaning up part of it. Remember over here, again, FOIL first and then distribute the two through. We will avoid a lot of mistakes if we do it in that order. Okay, so foiling, I get x squared plus 6x plus 9. Distribute the two through. Combine my like terms. Final answer, 2x squared plus 12x plus 17. In the middle, there wasn't a lot to do. You didn't have to FOIL it. You didn't have to distribute. No, nothing. Just combine my like terms. Negative 1 plus 3 gives me 2x squared plus 2. Do I need to do any sort of factoring or anything at the end of this? No, you don't. You are just putting them together. I'm not asking you to pull anything apart. Notice I have not talked about factoring anything. Okay, so just stop there. Yes, it has a GCF. I get that. We don't need to do anything with it. All right, the last part of this, I don't know if you've noticed, all of the ones we have done so far have been f of g of x, g of f of x, and we have x's in our answer. We don't have to do it just at x. They can ask us to evaluate this for a number. So there's a couple ways we can attack this. F of g of 2. If I've already done the work to do f of g of x, if I already did f of g, which we happened to do, I can just come over here and now plug 2 in for all my x's. That's all it's asking me to do. But if I haven't done this work, you don't need to. Okay? So yeah, use it if you did already for part of the question, but if you didn't do that, there is a second method. And the second method is this. It is plug in and then plug in. So I can take this 2 and plug it into G. I get a number answer, and I take that number answer and I plug it into F. Jordan.
So parentheses with a number that would not be multiplied by in.
Right, yes, it means plug in. So we can go G of 2, which gives us an answer of 5. That becomes what I then plug into the first function. So now I come over here, that answer is what I plug into F. And we would get a final answer. Let's see, that would be 25 times 2 is 50, minus 1 is 49. Now, when do I want to use that? Well, I would use that at all times unless I've already done this work. Okay, and they could make that a like multi-layer problem. Look at how something like this could look. G of F of G of 1. Okay, they can do something crazy like that, and that is a composition of a composition, where you would plug G into F and then plug that into G, which would be crazy. Now, we would never do that with X's, but they might do it with numbers, and that's where I just start at the inside. Okay, so I would do G of 1. G of 1 would be 4. So then I would do F of 4, because that's what this answer is, right? And so F of 4, let's see, 16 times 2 is 32, minus 1 is 31. So then I get 31, and I would move back out to the outside and do G of 31. Plus 3 is 34, and we would get a final answer of 34. So you don't have to do like crazy amounts of work. It's just plug in from the inside out. Questions on that? Okay, what we've looked at so far are all been polynomials. Not everything we work with is going to be polynomials, so we have to remind ourselves real quick of those 3 different domain restrictions we have, because domain restrictions don't go away. They will show up within compositions as well. If you remember your domain restrictions, great. If not, give yourself a reminder. Fractions is one of those. If I have something in a fraction, that means my denominator cannot equal 0. Today, you don't really need to get all the way to the whole interval notation thing, where you can just look at it as the inequality or the not equal to. But just a reminder of what our rules are. If it is a radical, what is underneath our radical has to be greater than or equal to 0. So in this case, x would have to be greater than or equal to -1. Or a radical in the bottom of my fraction, that would say that what's in the radical has to be just greater than 0. So remembering the difference in how we set up each of our domain restrictions. And the last part of what we're talking about today is where and how do we find domain restrictions in compositions? Compositions are a multi-part process because you've got a function at the beginning that you're plugging into another function. Well, finding their domain restrictions is a multi-part process as well. And it's kind of a continuous process as we work our way through a composition. Okay, so let's talk about how do I attack the domain of a composition. There are 2 specific places I would tell you to look at. The first thing you need to keep in mind is the second function. The first thing I would check is the second function listed. If that has a domain restriction, it's one of our possible domain restrictions. Okay, so the first thing I check is g of x. Then after that, I take into account the whole thing. Second, I would check the composition itself, f of g. Notice nowhere in there do I have to look at just f, and you will never have to look at just the first function. You'll look at the second function, and you'll look at the combo, the composition. Well, if we look for domain restrictions at multiple points throughout, we might get more than one domain restriction. So how then do I pick what the overall domain restriction is going to be? So I have an example here. What if we checked g of x and it gave us a domain restriction that x had to be bigger than 1? And then we did our composition and we got a second domain restriction that said x had to be greater than 3. Well, what you want to do is you want to compare those to each other and say, okay, of those options, which one is the most restrictive? So how do I figure that out? If I look at them on a number line, x being greater than 1 would be an open dot at 1, shaded all the numbers bigger than 1. X being greater than 3 would be an open dot at 3, shading all the numbers greater than 3. To pick the one that is the most restrictive, to pick the one that would work for both, we are going to pick the one that shades the least amount on our number line. Okay? Because what happens then is it takes care of both things that have to happen. So in this case, that green right there, that is the least amount. That is the most restrictive. The least amount on our number line is the most restrictive. The overall one we would pick is that x has to be greater than 3, okay? Think about that. If the numbers we can use have to be bigger than 3, are they going to be bigger than 1? Yeah, and that's why I picked the more restrictive one, is it takes care of. Check. If it's bigger than 3, it has to be bigger than 1. That one's already taken care of. That's why we picked the one that shades the least amount on our number line, okay? All right. We only have 2 examples today, okay? So here's your first of the 2 examples that involve domain restrictions. This one's a pretty simple one. Find f of g given f of x equals x squared minus 2 and g of x equals the square root of x minus 3. So remember, it is a 2-step process. First, we are going to check g of x, and then we'll go do our composition, and then we will check a second time for a domain restriction. So we're going to check g of x for a restriction. G of x, fraction, radical, radical in the bottom of the fraction, radical, okay? And our rule says that what's underneath the radical has to be greater than or equal to 0. X has to be greater than or equal to 3, okay? Now we just hang on to that. That's not our answer. That's a restriction on this problem, okay? We're supposed to go do this composition. So now I'm going to go over here and actually do the problem, which is f of g. So I'm going to take g and plug it in for all the x's that are in f. Okay, there's f, x squared minus 2. Plug g in where there was an x, and clean it up. Right now, it's still just a radical. It's the exact same one we have over here, so that's nothing different. When I clean this up, do you guys remember that squaring and square rooting are opposites of each other? So that's just going to go away, and I get an x minus 3 right there. Okay. And put that together, put that together, and I get x minus 5. And I check again. Fraction, radical, radical in the bottom of my fraction? Nope. So no more additional domain restrictions, which means I only have one, which means it wins. That is the domain restriction for this problem. So I like this problem because if I were to just look at the answer for f of g of x, it doesn't look like there's a domain restriction, and it looks like we should be able to plug everything into this. But we can't, because I can't plug numbers less than 3 into g. So if we were to go back to the beginning, and I said I wanted you to plug -7 into this, well, I can't plug -7 into this. So we can't do the composition. So finishing out my answer, that's my answer as long as x is greater than or equal to 3. Taylor.
So is the only reason why we look for, why we check g of x or whatever is for the answer for the 4 part?
Yes.
Because we don't
Yes.
have 3 for the square root of x.
Right. We are only checking this for a domain restriction because sometimes it's going to disappear throughout the process, and we wouldn't see that there's actually a domain restriction on this. And we're just checking for domain restrictions at the beginning to see if it was ever there. Pretty much if there's ever a domain restriction in there, it's there even if it simplifies out of the problem. That's basically what's happening. Okay? So let's look at one more example. We're going to look at an example where we have more than one domain restriction and how we make our final decision on the overall domain restriction that we will list for our answer. Okay, so f of x is 1 over x, and g of x is the square root of x minus 1. Okay, so our domain restrictions. We start with the domain restriction of g of x, right? we have a domain restriction here, and that is a radical. Has to be greater than or equal to 0. X has to be greater than or equal to 1. We just hang on to this, and if that's all the domain restrictions we have, that's our domain restriction. Now we move on to doing our composition. Okay? So now I'm going to do f of g. F is 1 over x, and where there was an x, I'm going to put in g. Okay? Good so far? All right. Now, we have that on the back of our worksheet, and that says that we are not supposed to leave a radical in the bottom of our fraction, are we? So I would rationalize that. To get my final answer. And my final answer would be the square root of x minus 1 over x minus 1. Good so far? Okay, let's talk restrictions. At this point, if it ever shows up, it is a restriction, and that is that third option, a radical in the bottom of a fraction, right? And our rule for a radical in the bottom of a fraction is that x minus 1 has to be greater than 0. Or x has to be greater than 1. We actually have a third restriction on that one, and that's come from this, and this would just be a fraction, right? And our fraction says that the denominator cannot equal 0. X cannot equal 1. So now what we need to do is look at those three and say, okay, of those three options, which one is the most restrictive? That becomes the domain restriction for our answer. So if I compare those all side by side on my number line, okay, the top one, x is greater than or equal to 1, would be a filled in dot at 1, bigger than 1. The second one, x is greater than 1, would be an open dot at 1, greater than 1. The last one is that weird one where it's not equal to. Remember, that's the one where we put an open dot here, but it can be everything else. So it could be everything bigger than 1, but it could also be everything less than 1. And my question is, which one shades the least amount on that number line, right? Okay, well, clearly it's not the red one. The red shades a lot, like almost everything. So it's down to the green or the blue. Which one has the least amount of shading? The green one, doesn't it? Because of the open dot here. That's shaded right there, which is the tiny little difference between those two. So then your overall restriction for your answer, x has to be greater than 1. That's how we make our decision on which restriction, if more than one were to show up in the problem. Questions on that? All right. You are not always going to be prompted to do that, but you will need to always list a domain restriction if there's ever a domain restriction for a problem. So notice I remind you of that on there. Do domain restrictions for any problem with a restriction. I also remind you that if your problem involves adding or subtracting fractions, get a common denominator.